consider a particle that is approaching the Earth. Okay, as a particle approaches the Earth, remember that the particles tend to go in circles, right? They tend to circle magnetic field lines, right? If I've got a magnetic field, say, out of the page like this, okay, and I have a proton comes from the sun or something like that, okay, it's going to get in here into this magnetic field, and it's going to feel a force. In this case, the force is up the page, right? I'm going to draw some magnetic field up there, right? And this thing's going to spiral like this. And of course, if it comes in with some angle that's at, it's not perfectly perpendicular to the magnetic field, it just spirals around it kind of helically or helically, right? And then notice how this radius is decreasing. The radius is decreasing because the magnetic field, as you get closer to the Earth, these lines are closer together, so the field is stronger. Right, so it spirals in, and of course it strikes either it'll go this way or it could easily spiral this way, right, and strike the north magnetic pole or the south magnetic pole. And just specifically, it'll strike the atmosphere above that, right? And these particles typically come from coronal mass ejections. The sun, typically during like sunspot activity, it can hurl these large chunks of plasma at the Earth, and these things can do terrible things to our satellites and magnetically induce incredible potentials. And you could look this up and get the details, but I think in the 1800s there was an event, a coronal mass ejection that struck the Earth with sufficient energy we think that if it happened today, it would like destroy our the transformers, like every transformer, which is a problem because we don't have the capacity to build transformers very fast. They last a long time. We just replace them every now and then, right? So that's sort of interesting. Anyway, this is a picture of Northern Lights. This is a picture, they've time exposed this, and you can see that the stars have smeared a little bit in the time that the shutter was open. But also the image of this is blurry, and it could be because these Northern Lights have sort of shimmery, quickly changing features that this time lapse is sort of smeared, right? It's a bit like taking a long exposure picture of a stream, right? The water looks all the ripples and everything smeared together. Here's one maybe with a faster shutter speed. It's got more detail, right? You can see they look a lot like if you ever look at a waterfall underwater, which is something I've done because I thought it would look like this, and it does. But anyway, it looks like little curtains and stuff. Here's another one, right? Again, this is just a bunch of particles striking the atmosphere. These colors are the spectral lines like you see in chemistry class. Different spectral lines. Green is real typical. I remember in the 80s, there was a Northern Lights bright enough that I read a book by them. I mean, I remember thinking, this is so bright I could read. And then I have to say, look, I have to remember that I can read by these lights, right? And then there's red. I've never seen a lot of red in my life, but and maybe that's only something you could see with a time exposure. I just don't know. This is kind of interesting too. This is a bubble chamber, right? A bubble chamber, I think I want to say either liquid hydrogen or liquid helium. And they basically hold it at right about where it's about to boil, right? I think they heat it up above its boiling point. And then when charged particles go through the helium, it'll cause these little trails of bubbles, right? And so we can see this. You can also do like a cloud chamber, which is a similar idea. But notice right here, okay, you've got a little, looks like a ram's head like that. This is probably pair production. So this is probably a photon coming in here, a gamma ray, a really high energy photon. I don't know why I drew a dot there. Okay, and then it passed near some massive object to make it, possible with momentum. And it spawned an electron, an ordinary matter electron. And I'm just going to guess that this is the positron, right? A positron is an antimatter electron, and it's nothing, it's cool. It's your first antiparticle, but every particle has sort of an antiparticle, right? Anyway, so this is the electron. Notice that they, all I want to point out here is that they spiral in different directions because one is negative and one's positive, right? That makes sense. And then they spiral in, and that's because they're not in a vacuum, right? So their velocity is decreasing. Remember, r is mv over qb, right? And so as the velocity decreases, the radius decreases. They're slowing down. And then this one, I'm guessing this is the positron because it probably at this point annihilated. It encountered another electron and turned into a pure energy or something like that. Anyway, cool stuff.